All right, let's dive right into this explainer. You know, when we watch a rocket clear the tower, we're really just seeing the explosive finale of a massive, painstakingly precise manufacturing process. Today, we're looking past all that fire and smoke to see exactly how these orbital behemoths are built from the ground up, specifically through the eyes of an aerospace engineer.
We're going to walk step by step down the ultimate assembly line. First up, the engineer's weight dilemma, then machining the rocket skeleton, shaping and chemical processing, precision welding and assembly, moving on to engines, avionics and control, and finally, testing and launch.
Section 1. The engineer's weight dilemma. Battling gravity before the rocket is even built. To kick off our journey down the assembly line, we've got to face the biggest antagonist any aerospace engineer deals with: gravity. Before a single piece of metal is even cut or a strand of carbon fiber is woven, engineers have to make brutal, uncompromising decisions about mass. Every single gram matters. I absolutely love this quote from ULA CEO Tory Bruno. "A factor of safety is a factor of ignorance." It perfectly sets that high-stakes mindset on the factory floor. You only pad your designs when you don't truly know what's going to happen out there in the field. If you know the exact stresses a part will face, well, you build it to withstand exactly that, and literally not an ounce more. To put this razor-thin margin of error into perspective, think about an everyday tractor. A tractor might have a safety factor of 7, right? Meaning it's built to take 7 times its expected stress. But a rocket? It operates between a factor of just 1.1 and 1.25. Why so incredibly low? Because every extra pound of metal costs a pound of payload. You simply cannot afford the weight of just-in-case engineering. So how do we actually solve this dilemma? It really all comes down to your raw materials and making careful trade-offs between weight, reusability, and manufacturing complexity. ULA, for instance, relies on advanced 7000 series aluminum for an incredible strength-to-weight ratio for single-use lifting. SpaceX, on the other hand, opted for stainless steel. Yeah, it's heavier, but it offers the extreme heat resistance needed for atmospheric reentry and reusability. And newer players like Skyroot, they are completely rethinking the structure by utilizing ultra-lightweight carbon fiber composites.
Section 2. Machining the rocket skeleton, removing weight without losing strength.
Let's head over to the milling stations, where we start turning these massive, heavy plates of raw metal into a hollow, spacefaring skeleton. To survive the brutal forces of launch without weighing the vehicle down, engineers have to aggressively machine down these plates to an incredibly thin profile. Through subtractive manufacturing, giant custom CNC machines carve out a grid pattern, literally milling away over 2/3 of the raw material mass while retaining 90% of the structural strength. And get this, all those metal chips that are carved away, they're actually collected and recycled right back to the supplier. Now, the way we carve out that way is a brilliant workaround to the laws of physics. Back in the day, we used to carve these triangular isogrids, mostly because 1990s-era finite element analysis tools could easily calculate their forces. But today, our modern tools allow us to use rectangular orthogrids. These are stronger, lighter, and take 50% less time to machine. It's wild to think that the computing power of the era literally dictated the physical shape of the rocket's skeleton. Section 3. Shaping and chemical processing, forming and treating the pressure vessels. Okay. Once that grid is cut, we have to carefully curve those massive metal plates into cylindrical tanks. You'd probably expect this to be done by some fully automated robot, right? But this is actually where aerospace engineering meets pure human craftsmanship. Instead of using fully automated hydraulics, skilled technicians slowly bump press the material by eye on these massive 25-ton presses. They delicately potato chip the panels by hand, which is a fantastic bit of factory jargon for slightly curving it along its length. This highly manual operation ensures uniform strain and work hardening to avoid stress fractures. Afterward, the aluminum is left to naturally age at room temperature, which evens out any internal stresses. Next up, the chemical processing station. First, we plane and clean the machined panels, then dip them into a heated sulfuric acid edge. After a thorough rinse with deionized water, we inspect the thick, bronze-colored oxide layer that forms. This anodizing process is absolutely crucial to prevent catastrophic stress corrosion cracking. In fact, this protective layer is what gives rockets like the Atlas V their signature bronze color. Without it, the microscopic porosity of the aluminum would invite corrosion, and under the immense pressures of launch, even a microscopic crack means losing the whole vehicle. It's a true obsession with perfection. Section 4. Precision welding and assembly, joining the tanks without weakening the metal. So now we need to fuse these formed, chemically treated panels into perfectly airtight fuel tanks. But here's the catch. Melting metal fundamentally changes its mechanical properties, creating a massive weak point. Enter friction stir welding. This is pure engineering magic. The process fuses metals using intense mechanical friction, binding the materials together without ever melting them. By just stirring the metal together, we completely avoid creating a weakened, heat-affected zone, resulting in an incredibly strong, perfectly sealed pressure vessel.
But what if you're not using metal at all? For companies like Skyroot that utilize carbon fiber composites, precision assembly looks a bit different. They use a precise 4-axis robotic filament winding system to meticulously wrap carbon fiber spools into isotensoid domes. The software actively manages friction factors to prevent even a single thread from slipping, because one slipping thread can ruin the entire part. This method is so precise that it requires absolutely no heavy internal metal liners, even for cryogenic tanks. Talk about a massive weight savings.
Section 5. Engines, Avionics, and Control. Integrating the brains and the brawn.
With our pressure vessels assembled, it's time to integrate the avionics wiring, and of course, the massive propulsion engines, the brawn needed to escape Earth's gravity well. When we look at engine integration, engineering constraints dictate the design, and we see two totally different approaches to the exact same physics problem. You have the NASA approach, which prioritizes raw single-use reliability and deep space thrust by using just a few massive engines, like the F-1 or RS-25. Then you have the SpaceX approach, clustering 33 smaller Raptor engines together. This design intentionally allows for mid-flight failures and heavily factors into repeated reusability. Now, to actually steer all that explosive thrust, we install submerged flex seals. I know, it sounds absolutely crazy to put rubber inside a rocket engine, but these are specialized layers of high-temperature rubber and metal. Because they're tightly compressed under combustion pressure, they survive just long enough to allow the engine nozzle to actuate and steer the rocket, balancing the whole vehicle precisely on a literal pillar of fire.
Section 6. Final testing and launch. Proving the hardware before leaving Earth.
Finally, our fully assembled rocket is rolled out to the pad for its ultimate manufacturing exam. But before we ever spark an engine, we conduct a wet dress rehearsal. This is a comprehensive test where the rocket is fully loaded with supercooled cryogenic propellant to simulate launch day. We fill the tanks with freezing liquid oxygen and hydrogen to guarantee that our structural seals, our welds, and our carbon fibers can actually handle the agonizing thermal shock without a single leak. And when we do finally ignite those engines for a static fire, a staggering 450,000 gallons of water instantly floods the pad. Now, this isn't just for fire suppression. It's specifically designed to absorb the acoustic vibrations. Without this massive water dump, the sheer mind-bending noise of the rocket would reflect off the concrete and literally shake our perfectly manufactured hardware to pieces. What's absolutely fascinating as we wrap up this explainer is thinking about the future. As new composite materials and 3D printing technologies emerge, how will the intense constraints of rocket manufacturing evolve in the next decade? The brutal reality of gravity will never change, for sure, but the incredible, awe-inspiring ways our aerospace engineers manufacture solutions to beat it are evolving every single day. Something to think about.